Hi, I'm Ben-Yaakov. This presentation is entitled Ripple Cancellation in PWM Digital to Analog Converter, DAC. In many occasions, we do have to transfer some information from a microcontroller unit, and in some cases, the data is analog to be transferred. Now, we can do it either by a parallel port and then using an external DAC, a serial port, again with a DAC, or if the MCU includes a DAC internally, then of course we can get the analog. Another way, which is very convenient and very useful and inexpensive, you can use it with very simple controllers, is to use PWM. In this case, the information is embedded in the duty cycle, and then it can be shown, of course, that if the voltage, maximum voltage, the peak voltage is constant, then the output, the average voltage of the PWM can be found by the averaging over one period, one cycle. Then the average will be the peak value times the duty cycle. So by varying the duty cycle, you can actually transfer the information. This is very neat because it's fairly noise immune. And then, of course, if you use the Schmitt trigger, you can recover the signal. And this is a very neat, a very simple way. Now, to operate it, you do need a filter because you get this information. You like to have an analog, an average value. So you put a filter, and in many cases, it's going to be an RC filter, a single pole filter, which unfortunately has two drawbacks. Number one, it has a limited bandwidth depending on the RC. So for a step function of a step in the signal, you're going to have some rise time, deteriorating the speed of the change here. And also you're going to have a ripple, which of course is also dependent on the RC value. Now the bandwidth is of course a function of the RC, and it will be 1 over 2 pi RC, and from the bandwidth you can get the rise time. It is theoretically 0.35 over the bandwidth. So this is for the step. Now as far as the ripple goes, I'm doing here a small signal analysis, that is assuming that the ripple is small. In that case, we can assume that the shape is like triangular, and therefore the ripple, the voltage peak to peak, will be the voltage times T on over the slope, which is 1 over RC, and then we can eventually get that the ratio between the ripple and the average value is 1 over the frequency of the PWM, RC. RC is the filter, and this actually can be expressed as eventually the ratio between the ripple and the average value as 2 pi frequency of the filter divided by the frequency of the PWM, the carrier of the PWM. So obviously, in order to get low ripple, you like to have the PWM running at very high frequency. In fact, if the PWM running at high frequency, you can also increase the bandwidth of the RC filter. Here is an example. This is just from simulation. We have here a carrier PWM of 100 kilohertz. We have an RC, it's a 1 kilo ohm and 10 nanofarad, it's 10 to the 5th over 2 pi. And therefore, the ripple to the average is about 1. And if we look at the waveform here, this is the original signal, and the green one is after the RC filter. This is filtering the PWM, and we see here that for the low value we have here about 1 volt average, and also the peak to peak is also about 1 volt. So this is a pretty good approximation when the signal is small. Here we see an expanded scale. This is the ripple, and this is the average value. As I've already mentioned, the best thing to do is, of course, to increase the frequency of the PWM. However, there is a limit here, depending on the clock frequency of the controller. Because as you increase the frequency of the PWM, the resolution of the duty cycle will deteriorate. That is, you cannot have a PWM running at extremely high frequency with very high resolution, many bits, because eventually the bit cannot be shorter than a clock. So therefore, if the PWM is running at very high frequency, then eventually you'll have to get by lower resolution of the duty cycle. So there is a compromise that you have to do to select the highest PWM frequency for the resolution that you want. There is an application note by Texas Instruments that is dealing with this problem. They are referring for a fairly strong controller here that they have, and they are examining type of filters. One is a simple RC single pole, a second order double pole RC, and then a second order filter with an inductor. And they are showing that obviously, depending on the construction, you get different bandwidth. This is the bandwidth of the filter, and here they have different kinds. This is the first order, 10 kilohertz, 20 kilohertz, then this second, and then they have also a fourth order. And you can see that obviously, depending on the structure, you get different bandwidth. And here they're also showing the effect, of course, of the limited resolution. If you go to high frequency, then you may end up with a low resolution. That is, you'll have a stepwise response because the resolution of the PWM, the duty cycle, is just not good enough. They do have a high resolution PWM output in this particular controller, so they are showing it the advantage of this high resolution PWM. Now, the high resolution is obtained by probably by an internal clock, which is much higher than the basic clock of the controller. There is another way to improve the performance and reduce the ripple. And here I'm showing an idea that was published by Stefan Woodward. This is in EDN, the so-called Ideas for Design, or Design Ideas, in 2017, and it's called the Cancel PWM DAC Ripple with Analog Subtraction. And the idea is really very neat and relatively simple. The idea is that if you have the PWM and you have an RC filter, you can generate by an inverter a AC signal which is inverted, and therefore by adding this inverted signal to the original one, you can get a cancellation of the ripple, or at least partial cancellation of the ripple. So this is really very neat, and here is basically the idea. The original signal has a DC component to it. This is the original signal coming out of the PWM port, has an average, has an AC, and now by having a inverter and an RC filter, here you are not passing the DC, you are just passing the AC, and it is inverted. So this is the original AC, this is the inverted AC, and by combining these two, of course, the ripple effect of this and this can be partially, at least, cancelled out. So let's have a look at it a little bit deeper. If I look up by superposition this path here, I'll see a resistor, capacitor, and then these two to ground. And then if I look at this path here, I see this branch here, C1 to ground and R1 to ground, okay, by superposition here. So these are not exactly the same, okay, there's a difference. And I can also see that C2 would have some effect. Obviously, if C2 is very small, then I'm not contributing anything. Ideally, you like perhaps to have C2 very large, because then you'll have all the AC coming through here as it is, without any distortion. However, if C2 is very large, then it is actually contributing to the filter and actually limiting the bandwidth. So there is a fine balance here that has to be found in order to get the optimal performance. Now, this could be, of course, done analytically, but I've done some simulation to explore these possibilities. So here is the simulation circuit that I was using. This is generating a PWM by comparing a triangular waveform to the signal that could be either a step function or a sinusoidal function. I can choose between these. This is actually doing the comparison. This is just comparing the triangular wave with the signal. And so this is the main branch here, and this is just an inverter, and this is the second branch here. Now, the original values that I've used here is 1K, 1K, and this is 10 nanofarad, and the frequency here is 10 kilohertz. This is the modulation frequency. So here is a result. We see here the original performance when there is no ripple cancellation. That is, C2 is equal to 0. See quite a bit of a ripple here. Step response is pretty good, but the ripple is really killing you. It's just too much. And then I've changed C2 to 10 nanofarad. This is 1 to 1. This is 2 to 1. C2 is twice C1. And then 50 and 100 nanofarad for C2. Now, what we see is the following. Obviously, as the capacitor is becoming larger and larger, the ripple is becoming smaller and smaller. That's fine. This is the lowest ripple. However, it's deteriorating the rise time. And so we can see here that an optimum choice perhaps would be 1 to 2. That is, if the C2 is twice C1, that is 20 nanofarad, we see there is a little or some deterioration of the rise time, but the ripple is really, really down from here to here. And here I'm showing the performance with a sinusoidal modulation. This is without C2, that is without ripple cancellation. This is the original ripple. This is the original signal, and this is the signal, the output of the RC filter with the ripple. And here we see the output of the RC filter with different cancellation capacitor. The first one here is the original signal. The green one is the one with the C1 equal to C2, or C2 equal to C1, I should say, and the red one is twice. So again, we see that there is a deterioration of the bandwidth, and we see here now as a phase shift. And again, it seems that a C2 equal to 2 times C1 is kind of a good choice for this particular design. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.